Welcome back to the classroom. My name is Mr. Wong. Today we'll be going through the 2012, did I say that right? 2012, sorry, HSC Physics paper. This is question 30 worth 5 marks. This is going to answer Module 6, Inquiry Question 1, which is about how charged particles behave in a electric field or magnetic field. So the diagram shows the path taken by two charged particles where they enter a region of a uniform magnetic field. When we say uniform, it means the magnetic field strength is constant, as you can see from this value of 1 Tesla here. Okay, so we have path P and path Q. Okay, why do the paths curve in different directions? Okay, so you can see they move in different directions. Well, if we go by what we know of using the right-hand palm rule, where your fingers, that's your pinky, and your thumb here. Ooh, that's a very awful looking hand. Okay, so the direction of where your thumb is going, that's the direction of the positive charge. The direction of your fingers is the direction of the magnetic field, which in this case is into the page. And then the direction of your palm, all right, the face of your palm is the force. So if the path is going up the page here, that means your palm is facing upwards. Your fingers are pointing into the page. Okay, whoops. And given that the charged particle is moving in this direction towards the right, your right hand should look like the palm is facing up, fingers going into the page, and right thumb going towards the right hand side. In that case, path P is being created by a positive charge. Okay, so the movement of a positive charge. Whereas path Q, if we have a look, our fingers are still pointing into the page. Our palm is pointing down the page. And what you should notice is if we're using our right hand, our right thumb is actually pointing to the left. There's no way you can actually have it point to the right using that same configuration. So path P actually belongs to the motion of a negative charge. So that's the reason for their difference in curvature or curved path. It's because one is positive, one is negative. So P is a positive charge, while as Q is a negative charge. You could just simply say that you have two different charge particles, but it never hurts to go into a little bit more detail or be as clear as possible. Okay, next question. Why are the paths circular? Okay, so that is a good question. Now, we know from the way charged particles behave in a magnetic field. If you actually have a look, the direction of our charge, of where our charged particle is going, to the palm of our hand, if we drew it on a side view, that's our finger, that's the face of our palm, and our fingers are pointing out like this, the force is going like this. So when exposed to a magnetic field, a charged particle is always being pushed in a perpendicular direction. Okay, and it just so happens that that perpendicular direction will create this circular path. If you think about circular motion, the same idea is true. When an object is going tangentially in one direction, the centripetal force acts perpendicular to it and it's dragging it into the center here. So that's what we can actually say. So in a magnetic field, or when exposed to a magnetic field, we can write a B field. The moving charge particle experiences a force perpendicular to its motion. This acts as the centripetal force causing a circular path to form. And that's essentially why magnetic fields show this circular pathway, because the magnetic field, or the force of the magnetic field, ends up becoming the centripetal force that causes this tangential motion. And as we talked about with circular motion, if you have a tangential velocity and then a perpendicular force applied to it, that's the circular motion that we see. How do the properties of a particle affect the radius of the curvature of its path in a uniform circular motion? So there's two things. We already talked about the charge. So if we're looking at the charge of the particle, actually, let's just be a little bit more direct. So the formula to represent the motion. So if centripetal force and magnetic force, or if given the fact that a charged particle will experience a centripetal force, we can actually show for the equation centripetal force equals to 𝑞𝑣𝐵. That's the equation that we have here. So the V's can cancel out each other at one point, so we're left with one V here. That cancels that one out. And we'll be left with 1 over R equals to QV divided by M divided by V. If we inverse it, the whole equation, so MV over QB, that's the formula that describes the radius of the curvature. Okay, so what we can see from this equation, so from equation, or from formula, if mass or velocity was to increase, then the radius of curvature will increase. Okay, but if Q or B was to increase, then the radius is going to decrease. Now, in this case, because the question is asking you the properties of a particle, you don't actually need to quote this magnetic field strength. Okay, so if Q of particle increases, so does the radius of the curvature of that particle. If the mass of the particle or the velocity of the particle increases, then R will increase like that. The reason being is because MV are directly proportional to R, while as Q is inversely proportional to the radius. Okay, so that's one way of approaching how to answer this question. So that concludes our response here. If you found it useful in explaining how charged particles behave in magnetic fields, please give this video a like, subscribe if you haven't done so already, and I'll see you next time.